We're going to be talking about sequences in series, which is going to seem a bit mysterious to start with, but it's actually a pretty straightforward proposition, and it involves stuff that you already know. Honest. So the first thing, what these things are. A sequence is simply an ordered set of numbers. So for instance, when you learn to count, that was a sequence. 1, 2, 3, 4, and so on. Now a sequence could go on forever and ever, that is on to infinity, or it could stop after a certain number of terms. Say it's the sequence of all the numbers from 1 through 10, for instance. Now there are certain sequences that you may have heard of that do follow a pattern, but may not be easy to then recognize. One classic one is the Fibonacci sequence. 1, 1, 2, 3, 5, 8. 1 plus 1 is 2. 1 plus 2 is 3. 2 plus 3 is, get the idea? Meaning the two terms prior, that is 5 and 8, would be added together to get then the next term. These are just examples of sequences. Some sequences can be modeled using equations. For instance, if you're looking at 1, 2, 3, 4, well, that's a linear equation, isn't it? That has a slope of 1 and a y-intercept of 1. So you could write an equation if you felt like it to model that. So you could say that that has y equals x plus 1. That could be the equation that represented that. Now one thing to keep track of is a sequence is not a set of coordinates. However, they're often referred to using that same kind of idea. Meaning, if you're looking at a particular sequence, and let's say we're looking at the sequence that is 2, 4, 6, 8, and so on. That is, let's just say it goes ad infinitum. That is on to infinity. For reference purposes, we'll say that this is the term, and this is the number of the term. So that would be 2, which would be the first term. 4 would be the second term. 3 would be the third term, which means then we can write a relationship for the sequence in terms of the term number. Often we'll use n to represent the term number, and we'll use either, well, oftentimes I'll use a sub n, sometimes I'll use g sub n. It kind of depends on the situation. But you could say that a sub n, in this particular case, was equal to, this is where you have to be careful, this is the first term. However, if you're writing this, because if you recognize 2, 4, 6, 8, that's linear, so it's got a slope of 2, meaning 2n, and it's just like our x, right? Think of this term number as the x and the term itself as the y value, 2n, and then because when we're writing these, as a quick reminder, if we have to write a linear equation, we really need to look at the y-intercept, which happens at 0, x equals 0. So technically that would mean that we'd be looking at 2n plus 0, or just 2n as the equation for that. We'll talk about more of that later. It does not mean, however, that sequences necessarily need to be linear or some funny thing like a Fibonacci sequence. See if you can figure this one out. So if you're looking at 1, 4, 9, do these numbers look familiar? They're all of the form n squared. That is, if you take the term number, first term, and square it, you get 1. Second term, square it, 4, and so on. Now, sequence, simply an ordered set of numbers. A series is the sum of an infinite sequence of numbers. Please bear in mind, a sum means that we're adding. So if I was looking at the series, 1 plus 2 plus 3 plus... I found this on the web for series as the sum of an infinite sequence. Sorry, Siri interrupted. In any event, 4 plus... Now technically, this would go on forever. So a series would be the sum of an infinite sequence. So if we had the sequence 1, 2, 3, 4, the series would be the sum of that. Now, this is not that useful because if you added up all these numbers, and now it does say infinite sequence, meaning that it goes on to infinity. If we added this up, well, that would be kind of boring because if you add up an infinite number of numbers, you get, well, infinity. This keeps going on and on forever. Now, there are going to be some interesting ones when we add up the infinite series, but more useful and more frequently we'll talk about something called a partial sum. Now, this is the sum of a subset of a series. So, for instance, let's say I wanted to find the sum of 1 plus 2 plus 3 plus 4. Well, that's easy. That's 10. That does not represent that whole series, because a series by definition is infinite. Sometimes they call it an infinite series. But it does represent a subset or part of that series. This can be written in a couple of different ways. You can use something called subscript notation. So subscript notation refers to the sum of the typo, the first n terms. So we're assuming that we're starting. So if you look at S, guess what S stands for, right? Sum of 5. We're talking that would means the sum of the first 5 terms. So let's say we're looking at our even numbers. That would be 2 plus 4 plus 6 plus 8. 2, 4, that's 4 plus 10, right? That could be written as S sub 5, because remember, this is the first term, first, second, third, fourth, and fifth. And when we add those up, of course, we get a nice number. 10, what do we get? 12 plus 12 plus 6, so 24. So we get 30, right? So that would be the partial sum. Another way to write this is using something called summation notation. And you guessed it, these are going to be used at you, on you, with you, and you'll learn how to use them as we go through some practice problems. This is a Greek letter sigma, particularly a capital letter sigma, which stands for the sum. So that's defined as the sum. That's what summation notation is. It uses the whole sigma thing. Now, here's how this would be written. Let's say I wanted the sum of the first 5 terms. Well, that would mean I would want to say the sum from, and I is a very popular letter for this, I equals 1 to 5 of, well, 2n. Now, particularly for sum form, we have to have some way of writing what the equation is that represents the particular sequence or series. So this means that this 2n, that's my even numbers, right? So that's the equation for my even numbers. Even numbers. Now we're going to look at particular techniques for finding these things, but this is the same as what we did when we found S sub 5. S sub 5, which was the whole 2 plus 4 plus 6 plus 8 plus 10. Now I just realized I made a slight mistake here. I should say n equals. The reason is I've got n here, I've got n here. That means I put 1 in for n. 2 times 1 is 2. And then it's sum, that is, it increments up, adding the next term. So this would mean this is my n here, right? That's 1, 2, 3, 4, and 5. That would tell me what the particular terms are, and then when I add them up, I get the same thing as when I found S of 5. Another way to do this would be that we say n, instead of starting at the first term, let's say we started the 27th term, and we added all the way up to the 53rd term of some sequence. I don't know, how about n squared, just for argument's sake. Now I don't know what that particularly is, but this represents the sum of terms 27 through 53, inclusive, right, of n squared. We're going to look at algebraic techniques that help us find these sums, but remember, the 27 to 53rd term, that is when you plug 27 in, so 27 squared is a number, plus 28 squared, plus 29 squared, plus 30 squared, all the way up to 53 squared. So this would start off like 27 squared plus 28 squared plus blah, 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 blah. Toward the end, it would look like 52 squared plus 53 squared. And this would be some really big number. We're not too concerned about it right now, just how do you actually interpret what this is asking you to do. So, quick recap. Sequence, an ordered set of numbers, counting numbers for instance. They can be related sometimes by an equation. For instance, the even numbers 2n. A series. By definition, a series is always infinite, okay? But that's simply, a series is when we add up a sequence. But more of what we will be focusing on is something called a partial sum, that is looking at the sums of a part of, usually starting at the first term, but not always, of a particular sequence. Sometimes it's written using subscript notation, S sub 5, and sometimes summation notation with our funny little Greek sigma.